Hello everyone and welcome back. So in today's video lecture, we are going to be covering a concept called infinite limits. So to get us started, let's go back to finding a limit using a graph. This is the graph of y equals 1 over x squared, and we're going to find each of these limits. So starting with the limit as x approaches 0 from the left of 1 over x squared. What this limit is asking is what are the y coordinates doing as x gets closer and closer to 0 from the left? Well, if you trace the graph to the left of 0 and get closer and closer to 0, this graph is increasing forever and ever, and there really should be an arrow on both of these ends right here. And so the y-coordinates are continuing to increase forever and ever and ever as we get closer and closer to 0 from the left. So to indicate that the y-coordinates are increasing forever and ever without bound, we're going to say that this limit is equal to infinity, meaning that the function is just increasing without restrictions and without bound forever and ever. Now for the next one, for the limit as x approaches 0 from the right, we are looking at what are the y-coordinates doing as the x-coordinates get closer and closer to 0 from the from the right. So if you were to trace this graph from the right of 0 and get closer and closer to 0, you will see that again, the y-coordinates are just increasing without restriction and without bound. So I'm going to say that this limit is also equal to infinity. So then, because the limit from the left is equal to the limit from the right, the two-sided limit as x approaches 0 of 1 over x squared is also equal to positive infinity. Now, if you remember the graph of 1 over x squared, if you take a look, what would happen if we actually did direct substitute 0 in the denominator? If you were to direct substitute 0 into the denominator, you would get 1 over 0, which I said in the last video is treated a lot differently than a 0 over 0. This is not indeterminate. This is just straight up undefined. And if you remember anything about this graph has a vertical asymptote at x equals 0. So it is no accident that it has a vertical asymptote at x equals 0, and the limits as x approaches 0 on either side came out to some sort of infinity. Now, an infinite limit is what happens when your graph either grows arbitrarily large or arbitrarily small for all x's that are sufficiently close to some number a. So again, x doesn't need to be defined at a for the limit to exist, but if the y-coordinates f of x are growing arbitrarily large for all x's that are sufficiently close to, but not equal to a, then we say that the limit as x approaches a is equal to infinity. Now, if the y-coordinates grow arbitrarily small, then you can also have a limit equaling negative infinity as well. So in short, an infinite limit occurs when the function either increases or decreases without bound as x approaches a certain value a. So the graph is going to either approach positive infinity or negative infinity as x approaches a. So in these two graphs at the right, they both happen to be approaching the same sign of infinity on either side of a. In this case up here on the top, as x approaches a from both sides, the graph is growing arbitrarily large, so the limit as x approaches a for this first graph is going to be equal to positive infinity. Now for this next one, the y-coordinates are growing arbitrarily small. They are decreasing forever without bound as x approaches a from both sides. So the limit as x approaches a of this f of x is going to be equal to negative infinity. Now, this is not always going to happen. It is possible for f of x to approach different signs of infinity on either side of x equals a. So it would look something like this. At x equals a, from one direction you would have, it approaching negative infinity, and then from the other direction it could approach positive infinity, and vice versa. So it is possible to approach different signs of infinity on either side of x equals a. Now, in all of these graphs, both the ones that, in the pictures and the one I just drew, these are all vertical asymptotes. So when you first learned what vertical asymptotes were, either in college algebra or in pre-calc, you learned them at the time as a value that a graph approaches but never actually reaches. It is a line that a graph forever gets closer to without ever actually crossing. The actual technical definition of vertical asymptotes actually involves infinite limits, and we're going to get to that in a little bit. So an infinite limit is going to occur on either side of a vertical asymptote. Now you can have one-sided limits that are also infinite, especially for graphs like natural log, for example, that only approach a specific value from one side. If you remember the graph of natural log, it looks something like this. It's got an infinite limit at x equals 0, and it only approaches 0 from one side. So the limit as x approaches 0 from the right of the natural log of x is going to equal negative infinity. So it is possible for a one-sided limit to be infinite. So this first graph right here, this is an example where the limit as x approaches a from the right of f of x is equal to positive infinity. This graph over here is an example where the limit as x approaches a from the right is equal to negative infinity. This graph here on the bottom left is an example where the limit as x approaches a from the left equals positive infinity. And this graph here on the bottom right is an example where the limit as x approaches a from the left is equal to negative infinity. So what I want you guys to do is take this graph of x over x squared minus 1 squared, and I want you guys to find each of these limits. So take a minute, pause the video, and find each of these limits. All right, so for the limit as x approaches 1 of f of x, well, x equals 1 is right there. And if you look on either side of 1, so as x approaches 1 from the left and from the right, the graph is growing arbitrarily large. The y-coordinates are increasing without bound, and we are approaching the same sign of infinity from both sides. So the two-sided limit as x approaches 1 of this f of x is going to equal positive infinity. Then for the next one, for the limit as x approaches negative 1, so this is going to be from both sides. This is a two-sided limit. Let's look at from the left and from the right. So from the left, we are approaching negative infinity. From the right, we are also approaching negative infinity. So from both sides, we are approaching negative infinity. Now, if you take a look at this graph, they are not drawn, but there are vertical asymptotes here at x equals 1, and again here at x equals negative 1. This graph will have two vertical asymptotes, and it's no accident that as you take the limit as x approaches those asymptotes, you get one of the infinities. Infinite limits are actually at the heart of vertical asymptotes, and the actual definition of a vertical asymptote involves an infinite limit. So definitely write this down because you are going to be using this a lot both on your homework and on the first exam. So if the limit as x approaches a of some function f of x is equal to positive infinity or negative infinity, or the limit as x approaches a from just the left of f of x equals positive or negative infinity, or the limit as x approaches a from just the right of f of x equals positive or negative infinity, then the line x equals a is called a vertical asymptote of f of x. So basically, if you take a limit as x approaches some value a, I don't care if it's from either one side or both sides, if just one of the one-sided limits comes out to some sort of infinity, that means x equals a is a vertical asymptote. So in rational functions, vertical asymptotes have two conditions. It's a number that makes the denominator 0. That's how you first learned how to find vertical asymptotes back in pre-calc and college algebra. And in order to be a vertical asymptote and not a whole, for example, the limit as x approaches a from either one or both sides must equal positive or negative infinity. So write down those two conditions because you're going to use them a lot. In order to have a vertical asymptote, the x equals a needs to make the denominator 0, and the limit as x approaches a from either one side, the other side, or both sides must equal either positive infinity or negative infinity. Now, both of these conditions must be checked in order to assume that x equals a is a vertical asymptote. You cannot just figure out what makes the denominator 0 and move on. Because if there is not an infinite limit at x equals a, that means you do not have a vertical asymptote. That means you have a hole in the graph. So if you take the limit as x approaches a and you get a real number, you have a hole, not a vertical asymptote. So that's why you have to check both of those conditions. So for this next one, this is we're going to take this graph of g of x here. And what I want you guys to do is I want you guys to, just from looking at the graph, identify the vertical asymptotes and then find each of these limits. So go ahead and pause the video and find each of these limits. Okay, so identifying the vertical asymptotes, we can see that we have one here at x equals 1. And we have another one here at x equals 3. So then finding each of these limits, let's start with the limit as x approaches 1. Now this is indicating from both sides, so let's look from the left and from the right. So as we get closer and closer to 1 from the left, looks like that's positive infinity. As we get closer to 1 from the right, that is also positive infinity. So the limit as x approaches 1 from both sides is equal to positive infinity. Now looking at the next one, the limit as x approaches 3 from the left. So here's x equals 3. We're approaching from just the left. So from just the left, looks like this graph is approaching negative infinity. So right away, x equals 1 is automatically a vertical asymptote. We can see it from the graph, but if you were to plug in x equals 1, it would make the denominator 0, and the limit as x approaches 1 was equal to infinity. So right away, x equals 1 fulfills both conditions in order to be a vertical asymptote. Now for x equals 3, if you were to plug in 3, you would automatically get a 0 in the denominator. So because it's a 0 in the denominator and the limit, even just from one side, equaled negative infinity, that was all you needed. That alone is enough to say that x equals 3 is a vertical asymptote. So you don't need both limits, you just need the limit from even just one side equaling some sort of infinity. It's automatically a vertical asymptote. Now for part D, let's look at the limit as x approaches 3 from both sides. So from the left, we approach negative infinity. Let's look at from the right. So as x approaches negative 3 from the right, it looks like we are approaching positive infinity. So the limit from the left does not equal the limit from the right. So the two-sided limit does not exist. That doesn't mean that x equals 3 is not still a vertical asymptote. This limit right there was enough to prove it was, but the overall two-sided limit does not exist. Now, finding limits out using a graph are really easy to do, but there is a way to find an infinite limit algebraically. So when dealing with vertical asymptotes, direct substitution is going to result in a denominator, in a 0 in the denominator. And you will get some other number besides 0 over 0. Any other number over 0 is treated a lot differently than 0 over 0. We're not going to be seeing a lot of 0 over 0s today. We're going to be seeing a lot of other numbers over 0, which any other number over 0 is just straight up undefined. It is not indeterminate. It is undefined. So I will say that finding infinite limits algebraically is a very intuitive process. You have to remember that a limit is what a function is doing near a point, not necessarily at the point. Like we saw in the last section, some cases they are the same, but in this case with vertical asymptotes, they are not the same. So you're going to be seeing this a lot. So yes, 1 over 0 is undefined. I am not arguing that. But you have to remember that a limit is what is happening near a point, not necessarily at the point. So this would happen when you just direct substituted. So you direct substituted some number that caused a 0 in the denominator, but not a 0 in the numerator. So you're not really looking at what's happening at that point. You're looking at what's happening near that point. So in reality, you don't actually have a true 0 in the denominator. You actually have a really, really, really tiny decimal close to 0 in the denominator. So what happens when you have some integer like 1 over a really, really tiny decimal close to 0 in the denominator? So what kind of number will we have? We'll have a really big number. So if you have 1 over a really, really, really tiny decimal close to 0, you're going to have a really, really, really big number, approximately infinity. So 1 over 0 can be approximated as one of the infinities. So in short, a not zero number over 0 can either be approximated as positive infinity or negative infinity. So you have to look at whether that really tiny decimal in the denominator is a positive tiny decimal or a negative tiny decimal. You also have to determine whether or not the number in the numerator is positive or negative. The signs of both the number in the numerator and that tiny decimal in the denominator will determine whether you have a positive infinity or a negative infinity. So, finding infinite limits algebraically is going to be very intuitive. So we're going to find each of these limits without the aid of a graph. So starting with the limit as x approaches 0 from the left of 5 plus x over x. Now if you were to direct substitute 0, you would get 5 over 0. This is not indeterminate, this is undefined. Which means that this limit will come out to one of the infinities. The question is, which one? Now we're approaching 0 from the left. So on a number line, numbers to the left of 0, those are negative numbers. So if you want to, go ahead and either mentally or on a calculator, plug in a really, really, really tiny decimal close to 0. Like, let's say, negative 0.001. And see what happens when you would plug that in. You don't really care about what the actual number you get is. All you care about is its sign, because this is going to be one of the infinities. It's just a question of, is it positive infinity or negative infinity? So 5 plus a negative decimal close to 0 is a positive number, divided by a really, really, really tiny negative decimal close to 0 is a negative. So a positive divided by a negative is a negative, so this limit is equal to negative infinity. So then for the next one, we're going to take the same function, but this time we are going to look at the limit as x approaches 0 from the right. So numbers to the right of 0 are positive numbers. Now remember, we're not actually looking at what's happening at 0. We're looking at what's happening near 0. So go ahead and if you want to, mentally or on a calculator, plug in a really tiny decimal, positive decimal that's close to 0, and see what happens. All you care about is its sign. So we have 5 plus a really, really tiny positive decimal is a positive number, over a really, really tiny positive decimal close to 0 is positive. A positive number divided by another positive number is a positive number, so this limit equals positive infinity. So I want you guys to try these next 3, so go ahead and pause the video and try these next 3. Okay, so for the limit as x approaches 3 from the right and the left. So this time, instead of looking at just positive negative numbers, you're looking at numbers close to 3. Now we're going to start with the limit as x approaches 3 from the right. So numbers to the right of 3 are slightly greater than 3. Now if you were to direct substitute 0, you get 2 minus 15, which is not 0 over 0. So this would be another not 0 over 0 case. This is not indeterminate. This is going to be one of the infinities. The question is, which infinity? So that's where the direction comes in. So the limit as x approaches 3 from the right. Numbers to the right of 3 are slightly greater than 3. So like, for example, 3.01. So go ahead, either mentally or on a calculator, plug in 3.01 and see what happens. All you care about is its sign. So 2 minus 5 times a number close to 3 is going to be a negative number, divided by a number slightly bigger than 3 minus 3 is a positive number, A negative divided by a positive is a negative number, so this limit equals negative infinity. So then for this next one, we're taking the same function and we're going to approach 3 from the left. So numbers to the left of 3 are slightly smaller than 3, like say 2.99. So go ahead and either mentally or on a calculator plug in 2.99 in for x and see what sign you get. So 2 minus 5 times a number close to 3 is still negative, divided by a number slightly smaller than 3 minus 3 is negative. Negative divided by another negative is a positive number, so this limit equals positive infinity. Now, the limit as x approaches 3 from both sides, because the limit from the left does not equal the limit from the right, the two-sided limit does not exist. Now, with vertical asymptotes, x equals 0 is a vertical asymptote of 5 plus x over x because even just one of the one-sided limits came out to infinity. Doesn't matter that they weren't the same on both sides, even just one of those one-sided limits being infinity was enough to say that x equals 0 is a vertical asymptote. Now for the next one, for 2 minus 5x over x minus 3, because even just one of the one-sided limits came out to infinity, that means x equals 3 is a vertical asymptote as well. So for this next one, I highly recommend that you at least factor this one because there's a lot of negatives around and it looks like there's at least a couple common factors such as greatest common factor of x in the numerator and a greatest common factor of x squared in the denominator. So I do highly recommend that you factor this first because it is easier to see when you factor it. So first thing that I'm going to do is taking a look in the numerator, there's a greatest common factor of x in the numerator. And to make my factoring easier, because the leading coefficient's negative, I'm going to factor a negative x out of the numerator. So I've got negative x, and then that will give us positive x squared minus 5x plus 6. Then in the denominator, there's a greatest common factor of x squared, and because the leading coefficient is negative, I'm going to factor a negative x squared out of the denominator, giving me x plus 4. So then let's finish factoring. So we've got the limit as x approaches negative 4 from the right of negative x times x minus 2 times x minus 3 all over negative x squared times x plus 4. And let's simplify this a little bit. So first of all, the negative divided by a negative, those can cancel out. And then this x in the numerator can cancel out with one of these x's in the denominator. So that will leave us with the limit as x approaches negative 4 from the right of x minus 2 times x minus 3 all over x times x plus 4. So now let's take a look at our limit. So if we were to direct substitute for negative 4, you would get a number that's not 0 over 0. So because this is not 0 over 0, this is not indeterminate. This is going to be undefined. It's going to be one of the infinities. Let's figure out which one. So if we are approaching negative 4 from the right, be very careful with this. Numbers to the right of negative 4 are greater than negative 4. So a number that's close to negative 4 but slightly greater than negative 4 is, let's say, negative 3.99. So either mentally or on a calculator, go ahead and plug in negative 3.99 and see what happens. So we've got a negative 3.99 minus 2 is going to be a negative number, times negative 3.99 minus 3 is another negative number, over negative 3.99 times negative 3.99 plus 4 is going to be a positive number. So An odd number of negatives gives you a negative, so this limit is equal to negative infinity. So the main use for this is in finding vertical asymptotes. So we're going to find all of the vertical asymptotes of this graph, and we are going to verify that they are vertical asymptotes using limits. So the first thing that we're going to start with is we're going to start with the values that would make the denominator 0. This will give us our candidates for the vertical asymptotes. So the two numbers that make the denominator 0 are x equals 1 and x equals negative 1. Now, in order to verify that they are actually vertical asymptotes, we need to take some limits. So let's start with the limit as x approaches 1 of our f of x. Well, if you were to direct substitute 1, yes, you get a 0 in the denominator, but in the numerator, you get 1 minus 4 plus 3, which is also 0. So even if you can tell just by looking at it that 1 would make the denominator 0, direct substitute 1 in the numerator as well, because you will find that you actually get a 0 over 0 for this. Remember, 0 over 0 is handled a lot differently than any other number over 0. A 0 over 0 indicates that we can do some factoring here and possibly fix this. So let's do some factoring. So the denominator is a difference of squares. It is x minus 1 times x plus 1. And the numerator we can factor as x minus 3 times x minus 1. So there's that common factor that is causing the 0 over 0. So that will give us the limit as x approaches 1 of x minus 3 all over x plus 1. So after we simplify, let's direct substitute again. So we'll get 1 minus 3, which is negative 2, over 1 plus 1 is 2, gives us a limit of negative 1. So we just took the limit as x approaches 1, and we got a real number. That means x equals 1 is not a vertical asymptote. What is actually happening is that there is a hole at the point 1 comma negative 1. So because we took the limit as x approaches 1 and we did not get an infinity, this is not a vertical asymptote. This is actually a hole at 1 comma negative 1. So that leaves us with the limit as x approaches negative 1. And let's go ahead and use the simplified version because it'll just be easier. Now for the limit as x approaches negative 1, you will find that if you direct substitute negative 1, you will get negative 4 over 0. Now negative 4 over 0 is just straight up undefined. This is not indeterminate. This is going to be one of the infinities. And because you're going to have to do a lot of this on your homework and on the first exam, let's go find some one-sided limits. So let's take the limit as x approaches negative 1 from the left of x minus 3 over x plus 1. So again, approaching negative 1 from the left, numbers to the left of negative 1 are slightly less than negative 1, so we're talking numbers like negative 1.01. Go ahead and either mentally or on a calculator plug in negative 1.01. Remember, all you care about is its sign. So negative 1.01 minus 3 is a negative number. All over negative 1.01 plus 1 is also negative. A negative divided by a negative is positive infinity. So that alone is enough to say that x equals negative 1 is a vertical asymptote. If even just one of the one-sided limits comes out to an infinity, you have a vertical asymptote indisputable. Now, for the other side, just to be thorough for your homework purposes and for the exam purposes, let's take the limit as x approaches negative 1 from the right of x minus 3 over x plus 1. So numbers to the right of negative 1 are slightly bigger than negative 1. So we're talking numbers like negative 0.99. So plug in negative 0.99 mentally or on a calculator and see what happens. So negative 0.99 minus 3 is a negative number. Over negative 0.99 plus 1 is a positive number. Negative divided by a positive is a negative number, so negative infinity. So, because the limit from the left did not equal the limit from the right, the two-sided limit does not exist. But that doesn't matter, because one of those one-sided limits came out to be infinite. X equals negative 1 is your vertical asymptote. And remember, x equals 1 was a whole at 1 comma negative 1. Now you can use this same process with trig functions as well, especially things like cotangent, which can be written as a fraction in terms of sine and cosine. Now you just have to remember that with trig functions, you're looking at angles and you're looking at what quadrant angles are going to be in. So the first thing that I'm going to do is I'm going to rewrite cotangent in terms of sine and cosine. So cotangent is actually cosine of theta over the sine of theta. So like with any other limit, you should try direct substitution first. So direct substitution gives you the cosine of 0, which is 1, over the sine of 0, which is 0. So this is undefined. This is going to be one of the infinities. This is not an indeterminate form. So since theta is an angle, you do have to think of the unit circle, and theta is approaching 0 from the right. Well, this right here is theta equals 0. So numbers that are to the right of 0 are positives. So thetas that are to the right of 0 are actually really, really small angles, just barely positive. So we're actually looking at a really, really, really small angle close to 0, but that is also positive. So a really small positive angle close to 0 is here in quadrant 1. So in quadrant 1, cosine is positive. In quadrant 1, sine is also positive. So positive divided by a positive equals positive infinity. So then for the next one, for the limit as theta approaches 0 from the left, again, we're going to rewrite cotangent in terms of sine and cosine. This time, we're looking at negative angles because numbers that are to the left of 0 are negative. Negative angles are actually in this quadrant here. They open in a clockwise direction. So a really, really small negative angle close to 0 is actually in quadrant 4. So in quadrant 4, cosine is positive, but sine is negative in quadrant 4. So positive divided by a negative gives us a limit of negative infinity. So obviously, the two-sided limit does not exist, but because even just one of the one-sided limits came out to infinity, that means theta equals 0 is a vertical asymptote. So that is going to be it on infinite limits. For the next section, we are going to be looking at what happens when we take the limit as x approaches infinity. That's called the limit at infinity. So there can be some overlap between them, but we're going to get into that in the next video. So thank you all very much for watching, and I will see you all in the next one. Bye-bye.